Hello, chemistry students. I want to do in this lesson a quick overview of density. I know that you've done this before or should have in middle school and ninth grade physical science. So just a quick review of what density is and how we calculate that. So density is the mass per unit of volume of a substance. Actually, I'll start with this. Mass per unit volume of a substance. So that means it's different than how we talk about how heavy things are, because we could say a marble, a small marble, and a styrofoam ball that's much, much larger are both, we might say a marble seems heavier per unit of volume than a styrofoam ball, but the styrofoam ball has more volume and maybe they weigh the same, but the marble is in fact much more dense than a styrofoam ball. So it's that the mass per unit of volume. And the unit of volume that we use with density is cubic centimeters, usually for solids, or milliliters for liquids. So we can talk about the density of liquids as well as solids. There's two ways that we can find the volume. If you have something that's a perfect cube, you can measure it and take the length times width times height of a cube, for example. And we can calculate the volume that way. But with irregular shaped objects, or even sometimes just smaller objects, it's easier to do the water displacement method. So most of the time for small objects, that's what we use, where we put water in a graduated cylinder. I measure my water level, maybe it was right here, and then I drop my little nugget of whatever I'm working with, and I measure the new water level, and then I find the difference between what it was before I added the object and after I added the object. And that change in volume must be because of the volume of my object. There's no other variables. So that's called the water displacement method. For those of you who cook, sometimes you might measure, I was taught back in the day in home economics class, that's how we measured shortening, actually, and fats like that. We actually used the water displacement method. I don't think they do anymore, but anyway, so density, we take the mass, so you have to find the mass by putting it on a balance, and then divided by the volume. So then the units we get are either grams per cubic centimeter or grams per milliliter, depending upon whether we're talking about a liquid or a solid. We also, it's helpful to know and important to know that the reason we could use cubic centimeters or milliliters is because these two are exactly the same volume. 1 cubic centimeter is the exact same volume as 1 milliliter. So if you had, and by the way, if it's water, it also weighs 1 gram, but that's true only of water. So water actually has a density of 1 gram per milliliter. The whole metric system is kind of based on water. So it's pretty cool that that works out. Of course, there's no correlations like that in the English system, so it's I don't know, someone did something right when they came up with the metric system. So that segues nicely into our next section, which is talking about the metric units, why they're easy to use. We're going to talk about the temperature scales that scientists commonly use, and we already kind of went over density. So in science, or scientists around the world use something called the International System of Units, or SI units. The reason it's SI is because it's French for something like Le Système d'International, and so we abbreviate it SI. But these are the standard units that are agreed upon, this universal system of measurement, which is really just a revised version of the metric system. The metric system just makes a lot of sense, and there's a lot of correlation between units that makes sense. We call it a base 10 system, and I know we talked about this earlier, so we just want to hit on it again because it's really important. I don't think we talked about all the different SI units, but we've talked about the metric system. So we use these in science, but sometimes, and we'll talk about why, non-SI units are preferred, and we'll talk about those sometimes. So again, a base 10 system. So what that means is, so these are the prefixes, kilo, hecto, deca. These are my, or the base units. Base units are liters, meters, grams. So we don't put a prefix in front of those, liters, meters, and grams. And then deci, centi, milli. And just to go through this really quickly, and I know you've seen this before. So if I have one, either meter, liter, or gram, if I want to convert that to decagrams, let's say this is grams, decagrams, I have to remember whole numbers have this understood decimal. I need to move the decimal over one place. So it becomes 0.1 decagram. I'm really dividing it by 10, right? When I'm going this way. A hectogram, 0.01, a kilogram, 0.001. Kilo means 1,000, so 1 becomes, I have to divide this by 1,000, which is becomes 0.001. Going the other way, now I'm multiplying by 10 every time I move this way. So 1 gram becomes 10 decigrams, 100 centigrams, and 1,000 milligrams. Be careful, it's really easy to accidentally move that decimal the wrong way. But as you can see, this is pretty simple to work through, and this is exactly why we use the metric system instead of the English system. If I were converting from inches to feet to yards to miles, it becomes just a very confusing and non-systematic way of converting. So if I have, you know, I don't know, let's say I have, you know, 150 inches, it's not easy to say, well, how many feet is that? Well, I know there's 12 inches in a foot. I probably need to get a calculator. I can't really do that in my head very easily. If I want to, you know, figure out how many inches there are, or how many, if there's 150 inches, how many yards that is, same thing. There's 36 inches in a yard, and so forth. There's, you know, you guys, most of you probably know how many feet are in a mile. A lot of you probably don't know how many yards are in a mile. So it's just the English system is just a really confusing system. So in science and around the world, most people use the metric system for everything, most countries. We are one of the very few that still use an English system. So when we talk about SI units, the SI units for length is a meter. Mass is a kilogram, but a lot of times we use grams because a kilogram is a pretty big unit, and if we're working with small things, we will want to use smaller units. Temperature is Kelvin, and honestly, we almost never use that. I shouldn't say we almost never. In common everyday science, we typically don't. In other applications, I'm sure they do. The unit of time is seconds. The amount of a substance is a mole. We are going to talk about that a little bit later in the year. Luminous intensity, how bright something is, technically candelas. Electrical current, amperes, and then energy. Maybe you talked about this in 9th grade physical science. We have joules or calories. When we talk about calories and food, we're really talking about kilocalories or 1,000 calories. A calorie is a tiny unit. So when we talk about terms of energy present in food, and by the way, that's why we express food in calories. It's like that's how much energy is available in that food when we eat it. But again, in our foods, we're really talking about kilocalories. They don't label it kilocalories on the food. They label it calories a lot of times with a capital C, which indicates kilocalories. In some other countries, they label both joules and calories. The SI units for volume are liters and weight is newtons. A lot of times, again, in general science, when we measure volume, we use milliliters. It just makes more sense. Weight is in newtons. You probably did some of that in 9th grade physical science with those physics concepts. With these, this is my rendition of a spring scale. So you hooked something on here, and then you lifted the scale, and the spring pulled down, and you could measure the weight in newtons. Remember, the difference between weight and mass is weight takes gravity into account. But that's why when we find the mass of things, we would never use a spring scale, because gravity is also working on that. But when we find the mass, we put an object on a scale, and then we slide these counterweights so there's like a little seesaw pivot point, and we move these weights until we've achieved equal mass on both sides, or a balance. That's why we call it a pan balance. And then the masses will equal, and then we just read what those masses are. All right, so then temperature scales. We said the Kelvin scale is actually the SI unit for temperature. However, it's not very useful for us most of the time. For some aspects of science, when we're studying gas laws and things like that, we do have to use Kelvin, but otherwise we really don't. And here's why. So let's say the freezing point for water is right here. On the Fahrenheit scale, that is, if you remember, 32 degrees Fahrenheit. On the Celsius scale, this makes a world of sense, it's 0. On the Kelvin scale, it's 273 degrees Kelvin. So it's already way, 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 way above 0. The boiling point then on these scales, remember on the Fahrenheit scale, so here's my boiling point, 212, 100, 373. So the cool thing, comparing the two scales, the difference between, looking at Kelvin and Celsius, so Fahrenheit makes no sense. There's just these these are just random numbers, not very useful, honestly. But of course, it's what we use. But there's exactly 100 degrees between the freezing point and the boiling point of water. There's exactly 100 degrees between the freezing point and the boiling point of water on the Kelvin scale as well. But the Kelvin scale is based on something called absolute zero. So the 0 point on the Kelvin scale is way down there. And absolute zero is the point at which molecular motion is believed to stop. So we tend to use this Celsius scale in science more than the Kelvin scale. And a Kelvin thermometer, if you think of a thermometer that had to have this many degrees on it, would be very large and very cumbersome.